So welcome everybody to the paper reading group, and we've had a fair share of technical difficulties today, but I hope that's the last of them. So as part of our paper reading group today, we're looking at the MLP-Mixer paper, and I'm really excited that I'm joined by Dr. Habib today. Dr. Habib and I have spent the past, I think, a few days, almost speaking every day, a few hours, and just discussing the MLP-Mixer architecture between ourselves. And I'm really excited Dr. Habib is here with us today. Um, but before that, just a very quick pointer, just like every previous paper reading group, we still have this link, 1db.me/MLP-Mixer. So I believe I've posted that in the chat. Angelika has, perfect. Thanks, Angelika. So if I go to if I type in my browser 1db.me/MLP-Mixer, that will take us to a report, which is this paper reading group, MLP-Mixer with special guest Dr. Habib. And then towards the end, I could just write a comment and I could say test. So this is where we'll be using all our questions and answers. And this has been the format since the beginning. So we're just going to be using the comments here as we go to ask questions. So I won't be monitoring the Zoom chat. I won't be looking at the YouTube live chat. It's just very difficult to manage too. So we're just going to be using the comments here. So about Dr. Habib, really excited and welcome, Dr. Habib. I know you have a PhD in structural biology, and then you decided to learn coding, and like many others, ended up, being a part of the Fast AI family. And then you started Kaggle, and starting Kaggle was, I've seen your work, I've known you, I've followed you, I've been a big fan of what you've achieved through the years, and seeing you as current rank 211 with 4 golds and 8 silvers. I think the only next step is like a solo gold, and you'll be a Kaggle grandmaster very soon. And now you're working as an applied deep learning engineer at Genilia. So really excited to have you with us. Welcome. And if there's if I missed anything, and if there's anything you want to add.
Thank you. First of all, thank you very much for inviting. It's an honor to be here. Really, together with you. I also, I think our journey started in parallel. You started with the blog, I started with the Kaggle, and now we are kind of merging. Yeah, I'm really, yeah, this is my journey. I started from zero. Yeah, now I do deep learning. And as someone mentioned, I only need 1 gold solo medal, which is the hardest thing to become Kaggle Grandmaster. So I will, for next, I don't know, 1 or 2 years, I will try my best to get it. It's definitely very challenging for me, but we'll see. Yeah.
I'm 100% sure you're going to get it very soon. I think it's only a few weeks, if not, days away, but fingers crossed, and good luck for that.
Thank you.
So with that being said, as Dr. Habib mentioned, he and I have worked together before, and previously we were working on the Vision Transformer blog post. So something, I'll share this in the chat once more, but something which I didn't know until this blog post is that Dr. Habib's really skilled at making wonderful visualizations and making complex ideas look very easy. And that's something I've been learning from him. In every meeting that I meet with him, there's something definitely there to learn. And these are visualizations that Dr. Habib did make for us, and in this previous blog post, which ended up being really popular. And looking at the Vision Transformer that way was for me, it was very easy to look at these visualizations and then understand Vision Transformer from his perspective. And he and I have gotten together again. So I'll share the blog post in the URL once more. But this time we've gotten together again for the MLP-Mixer paper. So as a supplement to this paper reading group, please feel free to have a look at this blog post. Again, there's lots of beautiful visualizations from Dr. Habib as we go down. As we keep going down, so that's the architecture from the paper. But again, you'll see lots of similarities in terms of visualizations, but we've again made mixer layer really easy, and so you can have a look at every possible operation that goes inside the mixer layer. So we're going to be using these visualizations today, and we're going to be using reading through the paper to understand the MLP-Mixer paper. But something I did want to touch just before we started was as part of the MLP-Mixer paper, when the MLP-Mixer paper came around, the MLP-Mixer paper was introduced initially as a convolution-free network. So the researchers from Google, and it says so in the paper as well, that it's convolution-free. Do you need convolution? Do you need attention? Probably not, and that's when the MLP-Mixer paper came in. But there's also a line or text inside the paper that did mention. So there's a special text in the paper that does say, in the extreme case, so this is here. I'm really sorry, 1 second. Sorry, my setup is a bit different today. So it does say in the extreme case, our architecture can be seen as a very special convolution neural network, which uses one-by-one convolutions for channel mixing and single channel depth-wise convolutions of a full receptor field and parameter sharing for token mixing. So we'll understand everything what these things are, but I guess the main point right now is to see that the paper mentions that through some operations, through some constraints, the MLP-Mixer paper in itself would still be seen as a convolution neural network. What exactly those constraints are, Dr. Habib and I have spent hours and hours trying to sort of demystify what exactly those constraints are. And something that happened along the line was then Jan LeCun, he went in and he said, well, it's not exactly conv-free, and the first layer could be a per patch, fully connected could be a conv layer with 16 cross 16 kernels and 16 cross 16 stride. And then the MLP-Mixer layer in itself could be represented as a conv layer, to which then there was this really interesting competition that was hosted, which is Mixer is a CNN problem, which was an attempt to make the MLP-Mixer be implemented just by using convolutions, just by using the convolution operations. So I guess before we got started with this paper, I just wanted to give some background on how the MLP-Mixer paper has been really exciting, and yet at the same time, the deep learning community has been a little bit split on whether it is a convolution neural network or it's not. We feel it's pretty much like a touchy subject that just comes down to semantics. And as part of this paper reading group, then we're going to dive into every bit of this paper with Dr. Habib. So Dr. Habib, is there anything else that you wanted to add over here?
No, I think I don't have anything yet to add, but it's a nice background introduction to, you know, why there is so much buzz about this paper.
Yeah, totally. Thank you. So then let's get started with this paper. So something that we know, I'm just reading the abstract right now. Something that we know so far is that convolutional neural networks have been the go-to model for computer vision. But recently that's been changing. We just saw the Vision Transformer blog. So ever since the Vision Transformer came around, in our previous paper reading groups, we've looked at we've looked at transformer architectures, and we just discussed the conv paper as well. And since then, a new type of architecture has emerged, which is the MLP-Mixer. What this MLP-Mixer is, it's not using self-attention, it's not using convolution. It's pretty much just using MLP layers, which are fully connected layers and it's just using fully connected layers and a very novel way of using the transpose operation that makes things work. And by doing that, by using such a simple architecture, they're still able to get competitive performance with the state of the art. So they're still able to, with lots of pre-training and lots of infrastructure and compute requirements, of course, to get it to work, but they're able to still get it to work in terms of having a good, respectable accuracy and competitive to the state of art. So that's the background about what MLP-Mixer is.
A bit.
Sorry, Sayam?
I'm sorry, could you please zoom in a little?
Of course. Is that better?
Yes, thank you.
Hold on. Let me try and make it a bit better. So I think that should be fine now.
This is perfect. Thank you.
Okay, excellent. No worries. Thanks for pointing that out. So then as part of this paper is really, really easy to understand. It's not like a lot of complexity in this But it's about making things simple and yet getting them to work. That's what I was really excited to read about this paper. So if we go down into the architecture, I think Dr. Habib, did you want to quickly talk about the architecture and just present the paper as a high-level overview?
Yeah, I just want to also kind of unpack, rephrase what you said a little bit earlier. So so just to have a bigger picture. So far, before this MLP paper, we had two main ways to classify images, right? One was this convolution based, where we use convolutions. And this method, or the way convolution neural networks were around maybe decades, and everybody was using, and until like last year, I'm correct, right? The vision transformer came, which kind of said, look, we don't need convolutions. You actually just need attention and positional embeddings and just linear layers. And this vision transformers they kind of overtook convolution neural networks, and they are currently even ranked top 1 in ImageNet classification. So basically we have two categories: convolution networks and then transformers, right? And it was kind of interesting, right? Something new came, and then within next 6 months comes this paper, and their main claim is following that you actually you don't need convolutions, you don't need attentions, you don't need positional embeddings. You can get competitive performance, and competitives, I mean, they claim that their best simple MLP module has less than 0.3% accuracy than top vision transformer module, which is pretty impressive. So they come up with this very simple module, just MLPs. MLP stands for multi-layer perceptron. So if you're a PyTorch user, it's just an n.linear. And they say, yeah, that's pretty much everything what you need. It's and then obviously Aman already introduced all the argument that MLP are kind of convolution or not. So this is just a big picture from my point of view, that it's kind of a third way to classify images. And so the way how it works, just a global overview. Again, we will go into details. There are some parts which are very similar to transformers. So here, what you see that we have this image, we basically break down into the patches, right? Thank you, Aman. And these patches, right? And then we have this single shared linear layer. What we do, we flatten the patches and then we project them. So we convert them to a single vector. You can call it embedding, patch embedding, or you can call it latent representation. Doesn't matter whatever the terminology is. It's just a single vector. For each patch, we get single vector, and then these vectors, the combination of vectors, goes to this mixer layer, and we'll go in detail what's inside the mixer layer. But to be honest, what's happening, there is two MLPs there which do convolutions either directly on the patches or on the channels, and you have multiple layers of those, and at the end you take the mean, and then you have this classification ahead. So to be honest, it uses two building blocks, right? So it uses an n.linear, and then it uses GLU, which is activation function. And then obviously there is a dropout. I don't know if you consider it layer and skip connections. So it's very simple. That's pretty much it.
Yeah, that's really, I think if we were to explain the paper, it would take 5 minutes because it's that easy. But I guess the interesting bits that come from this paper is that even after being so easy, it's still able to perform very well with those very complex architectures out there that use like self-attention and I think that's why this paper is one of the first papers to do so, and then there's other papers that have followed. But something I would like to highlight is as part of this, then Dr. Habib mentioned we start with an input image. So let's say you have an input image like this. What we do is we break it into patches. So you're pretty much converting that into like small patches. And this thing has been explained very well in a previous one of our blogs in patch embedding. So I'm not going to go into the details of this. I'm just going to do a high level overview. But if you are to have a look at exactly what's going on in patch embeddings and how this thing gets converted into, how everything gets converted into a vector from a very detailed perspective, then I've shared that link again in that blog. But then coming back to from a high level perspective, then what happens is each one of these patches, like 1, 2, 3, 4, 5, 6, they're pretty much 9 patches, right? Each one of these patches is represented by a vector. So there's 2, and then that's the 9th one. So that each long vector is a representation of that patch. So think of it that the first vector is a representation of this small patch at the top left. So that's the first vector. Then the second vector is this representation of this part of the image. So that's the second vector, and so on. The 9th vector then becomes the representation of this part of the image. So that's just basically then, because a computer doesn't know, it can't read an image directly, you have to convert it into a vector or a matrix. So you pretty much get a matrix that's consisting of like 9 patches. It's just in this particular example. And then, as Dr. Habib said, it goes into the mixer layer. And in the mixer layer, there's some operations that we will look into, but pretty much an MLP, everywhere that you see or you will see in part of this paper, an MLP, that's exactly as Dr. Habib already mentioned. It's a first convolution layer, 2 convolution layers, and then separated by a GLU or non-linearity, basically. And fully connected then is pretty much in PyTorch, you could just say nn.linear, or in TensorFlow, I believe you could say dense. So I'm not a TensorFlow user. I could be very well wrong here, but I do believe dense should be what is a fully connected layer in terms of PyTorch and TensorFlow. So that's the main overall idea. I guess now the next step is for us, like from a high level perspective, then that's exactly what's going on. But then the next step for us is to understand this mixer layer, on what exactly is going on in the mixer layer. And let's start by doing that. Let's start by looking at things in a simpler way. So I believe, again, from the MLP-Mixer blog, Dr. Habib, I'll take that. I'll take your visualizations, because it makes things really easy to explain. So maybe figure 2, is that something that's going to help you explain how everything gets converted into a patch embedding?
Yes.
Should I copy paste in OneNote? So I can
Yeah,
scribble, or
whatever you prefer. Yeah. Okay, so we are right now. So what we will present to you is one forward path. So we'll take one image and we will go one by one each step to explain exactly what's happening. And then you can just apply this operation to millions of images. It will be the same. So in this case, we have image of the frog. Okay. So the step which we are describing is converting patch to some embedding vector. Okay, so this process is very similar to vision transformer. So this part is 1-to-1. So the way how it works, so we have image 224 by 224, and what we can do, we can divide this image into grid, or into the patches. So the patch which we will use, it will be 16 by 16. So if we do math, we will have 196 patches. So so here the first patch will be the top left corner, which is green, and then the last one will be this black one, which is 196 patch. It's located in the top right corner. And so if we'll now imagine we just break down the image and we have this 196 patches, and each of this patch will have dimension of 16 by 16, and we have 3 channels, right? Because images comes in red, green, blue, so we have 3 channels. So now what we're gonna do, we will take this. So we'll take this patch and we will completely flatten it. So 16 multiplied by 16 will be 256, and we have 3 channels. we have 3 channels. It will be 25, 250, 712,
768.
768. Sorry, 768. So we basically take the patch, we flatten it to 768. So each pixels will be like just a single vector. Okay, and then we do for all 196 patches. Okay, and then what we can do, we can in PyTorch we have nn.linear, which takes the 768 and we can project it to any dimension we want. So we can either do one-to-one measure, either we can project to 768 or to 512.
Yep.
Okay. So this is it. So it's a one shared layer, and we go through all the patches. So what we will get? We will get 196 for each patch and 768 vector. So it's, think about this, we will get a table, which 196, 768. So there is a terminology which I would like to say. So there, in the paper, they use channel mixing. Channel refers to the so for each patch we have, if we use the embedding dimension 512, so we will have 512 channels. If we use 768, we will have 768 channels. So channels will refer to a column in a vector. And then I believe tokens, Aman, correct me if I'm wrong, refers to the number of patches. So yeah, it's 190. Yeah. So basically you can say for each image, we will get token by channels or number of patches by embedding dimension. Yeah. Totally. Right. So this is the first step, and this is very similar to transformers. This is the only thing which is similar between transformers and MLPs.
Yeah, it's okay. So far, like until here, this is,
yes,
all of this from back on is the same as vision transformers. I'm just going to type with. Yeah, so this is exactly the same. So far, as Dr. Habib is saying, because you have, say you have an input of 2:4 by 2:4 image, and each patch, basically the height and width of this patch is 16 by 16. So you'll get basically 196 patches in total. And then each of these patches could be flattened, or it could be projected using this linear projection layer. So in the end, every patch becomes a vector here like this. So you can have every patch represented as a vector. The dimensions of this vector could be depending on this linear projection layer. It could be 512, it could be 768, it could be whatever we want it to be. But the main point is that until this point, then you get like this, you could stack these all vectors together. So you get a 196 by 768 matrix. So now your input image has been converted into a 196 by 768 matrix. Now, whatever happens after this point is what's different in the MLP mixer than the vision transformer. And that's what we're going to look at now.
Right. So I hope this part is clear. I mean, we tried to explain very nicely. I think after this, we will come back to this and explain, we are using right now nn.linear, but we will show you how you can replace the same operation by convolutions. But I think we will come back this towards the end once we go how exactly this is done in the paper. So Aman, should we move to mixer layer after this?
Yes, 1 second. So I was thinking for the mixer layer, I did have a way to explain the mixer layer.
Okay.
So let me. Or right. If it's okay if you want to go to it, Dr. Habib, you can definitely go through this mixer layer. I'll just copy paste this.
Yes.
Do you want me to copy paste this, or did you want to use your visualization?
I think I will use mine. I think this will be easier for me because, okay, so if we go down.
Is it this one?
Yes. Oh, yes, it's the first one. Yeah, so this whole thing, if you can copy paste, because this is the whole mixer layer, yeah.
Okay, 1 second. So I'll just copy this bit here.
Yeah.
Okay, 1 second.
Okay.
Is that what you want?
Oh, that's perfect. That's perfect, right? So in my case, okay, so we had, yes, thank you, Aman, for it's 512. So we use 512. I think there was a mistake in
Yes.
the image, and we will correct it later. So basically, we took this 768 patch. We took a patch, we flattened, and then we projected to the 512 dimensions. And so this we will refer them to channels. So for each patch have 512 channels, and we have 196
Tokens.
Okay, so so here what's something very interesting starts. So here's we enter to mixer layer. So mixer layer is something very simple. You always start with the layer norm. It's a type of normalization. I'm pretty sure you're familiar with batch norms. So layer norms is people prefer to use in kind of transformer-like architecture. It just normalizes all features between, I forgot, 1 and 0, or there is some arbitrary value. It doesn't matter. It's just a normalization layer. Okay. So there is first. So what we do. So first we will flip these features. We will have 512 by 196. Okay. So first layer called token mixing layer, and token refers to I believe it's across we mixed across the patches, right?
Yeah. Is it okay if I quickly make a visualization? And I know exactly what you're trying to say.
Yeah.
Okay.
Please.
I know exactly what you're
in.
trying to say.
Yeah. Yes.
Okay. So basically, because our input looked something like this, right? You had 196 rows and 512 channels, but because you stacked all the vectors together, because we don't want to forget what exactly was happening. So each patch then is a vector like this, right? This is the first, like all of this, the first line is just a 512 long vector. So what these 512 are, these are the channels. So that's what that's basically the embedding dimension, if you want to call it, or it basically means that you're representing a single token with 512 channels. So that's what this. But if you look at it, then every row is a token in this, like the input matrix of 196 by 512, which we are looking at this. In this input matrix of 196 by 512, every row is a token, which is coming from this patch on the left. So every row then is basically this representation of the patch. So patch and token are used in a similar way. Token is just a word of saying that the patch has been converted to a vector. So every row then in this case is again like that token, and then every column is basically a single channel. So you have 512 columns, which means you have 512 channels. But when you take the transpose, then you have 196 on the columns and you have 512 along the rows. So what that means is that every row pretty much now is a single channel. Every row is a single channel. So this is a channel. And then every column is a token. So a single token with all the 512 channels is basically this column. And then a single channel with all the 196 tokens is basically this row. Does that help, Dr. Habib? Is that exactly what you're trying to say?
You basically, we are looking for each position across the patches, across the tokens. So what? Yes, that's beautifully explained. So now what we have one linear layers, which takes there is something, but it takes 196 features. But just ignore for now the projection. But what it does, it takes 196 features, and at the end it returns 196 features. So it's a single shared linear layer. What we do, we apply across all the channels, we apply patch, and we kind of look across the patches first. It's kind of, think about this as a global view.
Can I jump in?
Look for. Yes.
Can I quickly jump in?
Feel free.
Yeah, I guess the main point then to look in this token mixing layer is that the mixing is actually happening along the rows, because that's how the linear layers do the mixing. The mixing always happen across the rows. So they'll take each row in one by one, and then the mixing is going to happen across the rows. But what does that mean when we say the mixing is happening across the rows? Which means we're mixing the columns, right? If you have a single vector like this, or a single token, basically this row represents a token, and then you have 512 channels, right? Oh, sorry, I wrote that wrong. In this, the rows are the channels. So you have a row as a single channel, and the columns are the 196 tokens. So when you're doing mixing along the rows, you're actually mixing these 196 tokens, right? Every single channel goes in as input, and then you mix the 512 channels. Every single channel goes as an input, and then you mix the 196 tokens. That's why this layer has been called as token mixing, because when you're mixing the rows, you're essentially mixing the tokens. Does that help?
Yeah.
I know I mixed the I
No.
messed the token and channel
Yes.
quite a few times, but I hope I was able to get the point across.
Right. Yeah. So right. Maybe Aman, you can just explain the next part because you explained so nicely.
Oh, okay, sure.
Yeah.
So then in the next part, then once, because we're mixing the rows in this bit, which means we're mixing the tokens, right? So now we're mixing spatial information in the image. So each token is being mixed with every other token, which means you're mixing the spatial information. But in a convolution, what we also mix is like the information that we need to add is also, we need to be able to mix the channels, because we also have cross channels. So all the previous papers like squeeze and excitation, pretty much, or even in a convolution, when you say the number of in channels is X and out channels is Y, you're actually mixing across the channel dimension as well. So what we do is then we take this output from the token mixer, and we do a transpose again. So when we do a transpose this time, we get 196 by 512. What does that mean? At this point now, every row becomes a token, and every column becomes a channel, just as when we started, right? So every row becomes a token, and every column becomes a channel. So then again, we pass this through the same sort of MLP is what it is called. We pass it through another MLP, but actually, as I've previously mentioned, and a fully connected will take in row by row, like one row in, row by row. And what it is going to do is it's going to do the mixing across the rows. So the mixing is actually happening across the rows. And what that means, that you're actually mixing the channels, because every column is a channel. So when you're mixing that columns, you're actually mixing the channels. So that's why this particular layer is called channel mixing. So the first layer is called token mixer, because you're mixing across the rows that are tokens, and then the second one you're mixing the channels. That's the key difference in the two.
Yeah. So just to get a global picture, you have patches. You're doing global and local mixing. This two operation basically perform the same. Kind of performing these things, and that's it. So yeah, this is the architecture, and then you get the output, which is exactly 196 512, and then depending on the configuration, depending on the configuration, we will you can have 10 or 12 layers, I forgot, and that's pretty much it. And then at the end, you just take a mean, and then you have this output layer which predicts number of the classes, and that's it. It's
Yeah.
really it's really as simple as it is. It's not complicated. Yeah. Yeah. So Man, do you want to add something to this?
Yeah, I guess I was also baffled when I'm used to like spending more time trying to understand the paper, and it takes me, because I'm very slow, it takes me longer to understand the paper. But when I was reading this paper, it took me like 5-10 minutes to understand what was going on in the paper, to understand the architecture. And I was like, okay, I must be missing something. There's something definitely, there's some detail I'm missing or something like that. But this is really it. This is really the MLP.
Yeah, and
You just do a transpose.
yeah, so now if we go a little bit down and so this simple thing can compare to transformers, so if we go down now to the paper, let's go to the table.
Did you mean the different architectures?
So this is basically, so this is basically a standard, your standard archive paper, which will tell you, look, we tested different version of this architecture, different different patch sizes, embedding dimensions, and so on, and they all kind of work nicely. There is nothing interesting in this table. It just shows you what they tested. So if we go down now a little bit, there is this okay,
is it this one?
Right, so this one, basically this it just shows comparison, so for example, so they try to do different pre-training tasks, and you can see, for example, if so, since it's Google, they have this GFT 300 million. It's a secret data set which only Google had access. So what they do recently, they just pre-train on this, and then they train on ImageNet. And you can see, the mixers has performance is 87.94, and on ImageNet, and then the Vision Transformer performs 88.55. It's really close, right? The Vision Transformers is very heavy architecture. It uses attention and blah, and it's complicated. But you can see that they get really very, very close performance, which is very nice, right? So if we go to Aman, do you want to add something here?
No, I think you've got this covered. Keep going.
Yeah. Okay. So one thing which I want to point out, that so they claim there's, if we look, right, so if there is one advantage of this MLP architecture. So imagine you're a company, right, and you want to deploy something, and I don't know whether you will care about accuracy or not, because the accuracy is so close. One thing about this MLP mixture is that it has extremely high throughput, so it can predict images. You can have, like, in some cases you predict 120 images through TPE or through GPU cores. And for example, for Vision Transformers, so if we look on the top, you can see that the mixer can predict 104, 105. Oh yeah, so in this case, which is a very heavy architectures, MLP mixtures are much more lighter, and they can predict, a lot of images, high throughput images. So if you're
almost 3 times, still 3 times the vision.
Right. So if you are interested in deploying the models, you might be thinking, like, maybe you don't need Vision Transformers. You can just, probably go just use MLP mixtures, and you have, depending on what's your objective. So this is one of the advantage. So if we go to the next slide.
Just the one thing I want to add here is the training times. So I know it says like TPU v3 core days, but one thing, when like this architecture, when it's pre-trained on ImageNet 21K, it's pre-trained on GFT 300 million. That just means that when you're using a simple architecture, you pre-train it on lots and lots of data. So you're actually pre-training on 300 million images. It's not like you take this simple architecture and then you take EfficientNet and you train both of them on ImageNet, which is 1 million images, and then you think that you'll still get comparative performance. That's not going to happen, because when you have a simpler architecture, you pretty much have to give it a lot more data for it to learn things, as compared to an EfficientNet that could have a very competitive performance just from the 1 million images. So in terms of like costs, yes, it's going to cost a lot to do the first training. But if you're definitely, as Dr. Habib says, if you're definitely a company that cares about the throughput, because it's a simple architecture, which means it can do things faster. Yeah, that's the only thing I want to add, is just the size of the pre-training data sets.
Right. So then if we go down, there was one more. So yeah, this graph. So, I found, so for example, they also make really nice points. So if we, so this, you see this on the right graph. So this is very interesting. So, there is something called scaling. So they did very simple experiments. So they use Vision Transformers and mixers. And, so what they did, they, instead of training on 300 million images, they first trained on 10 million. and then they measure accuracy on ImageNet. And so yes, so you can see like, so this is on 10 million. And if we go to the 30 million, the vision transformers, you can see it's kind of plateaus a little bit. So there is no difference between 30 millions and 100 million. It's kind of, you will get the same accuracy. But in the case of mixers, what's interesting, the more data it has, it kind of goes kind of linearly, the better its performance. So it requires a lot of data to train. So this was also one of the points which author making, that perhaps if you have a bigger more data, so it scales by the data. So if you provide more data, maybe we will see better performance than vision transformer or so on. And you can see for vision transformers, it's kind of after 30 million, it's kind of flat. So just to sum up, it's lighter architecture, it has high throughput, and it scales with the pre-trained data. I think, which is very interesting and nice property.
Yeah, definitely.
Okay, yeah. Okay, so let's go to the next, not this one, but the shuffling thing.
Yeah.
Yeah, so this, okay, yeah, this is just
I'm trying to find where is the shuffling. This is, so this is just the table that's just comparing the results, right?
Different. It's just a bigger table which compares different architecture.
This is just showing like the weights and visualizing the, like, because it's just linear layers. I think the point here is like you can make it's easier to look at all the weights, and you can understand the architecture better because it's so simple, and simpler things are easier to understand.
So here they want to make arguments, the weights, you can draw them, and there are some, if you see there is this thing that in CNNs, early layers are responsible for recognizing small features, and then as you go, there is some global features. So they are also showing that this they were curious whether it worked in the same way as CNN, and there are some evidence. You can see there are these filters in this in this linear layers, and they have like so red means negative number, blue means positive numbers, and in the early layers it just they're focusing on something, but as as you go to the a little bit later layers, you can see there is some kind of complex patterns emerging which they try to recognize. So that's pretty much it, yeah. In this.
I just want to add context. Yeah, I just want to add context. Where Dr. Habib mentioned that like it's similar to CNNs. There's this paper visualizing CNN layers by, I guess that's the paper, Zeiler and Ferguson. I believe that's the one. So I just want to quickly find that paper. It's this one, visualizing and understanding convolution neural networks. In this paper, you will see basically that the patterns are very similar to MLP-Mixer. So I just want to add context, like that's the paper for anybody watching this after.
Yeah. Okay. Yes, and there is also very nice Distill articles about different visualizing filters of neural networks. Just in case somebody wants to read. Okay,
so if we find the mixing,
right?
Where did that go? Hold on. Is it after the role of model scale, the role of pre-trained? That's related work. Conclusion. Is it in the experiments at the bottom?
Maybe
it wasn't. Let me just Google quickly search for it here. What was it? It was called shuffling.
It was shuffle. Yes.
Oh, here it is.
Here. Okay, so that's something very interesting. But it's not surprising. So so this is ablation study. It's very interesting study. So they did 3 experiments. We took original images. Actually, somebody on the chat already asked questions about what will happen if we change the order of pixels or the patches, right? So this is the exact experiment what they did. So we have 3 sets of experiment. We take original image, and then feed it, train on original image. And then what we do is that we take the patch, we shuffle the patches, and then we shuffle pixels within the patches. And then the third experiment is that we just take image and just randomly shuffle everything, right? So on the left, you will see the result for the mixers, because it's used nm.linear, so original. And when you shuffle the pixel, the patches and the pixels inside, it's actually, it doesn't care, because it's just linear layers, right? They don't care about the position because everything is connected to everything. And you will find the same, you will find the same, you will find the thing. But when you, and the performance is the same, right? But in the case of ResNet, if you take the classical ResNet, so in original they are fine, but if you shuffle, the patches and then you shuffle the pixel within the patches. So again, this is uses ResNet. It doesn't care about patches, but just to be consistent. And you can see the performance immediately drops because ResNet cares about the order of the pixels and where they are located. I think it's called inductive bias, if I am correct.
Yeah.
And then, for example, and then the bots suffer from global shuffling, but it seems like MLP does better. I don't know the scale. Yes, MLP does better, right? Because it's more than 20, right? In some cases, and this, in the case of ResNet, it's never goes below.
So does that then is it easy then,
Yeah.
Dr. Habib, is it easy to say that it can handle corruptions better, the MLP-Mixer? Or is it like it can handle noise better, or is that a tough to make inference?
I think the point what they want to say that this that MLP probably doesn't care about order so much. However, this ResNet or vision transformers, they suffer from inductive bias. They care about order. So maybe it's much more robust, but I'm very afraid to make this kind of statement. So I will just say what I see from this experiment.
Absolutely, keeping it safe.
Yes.
Let me have a look at the questions if there's any. Oh, sorry. Yeah, keep going.
So I want to do one. What's a why? Okay, yes. So let's go to figure 5. Can we go to figure 5
yep.
on sub?
This,
this on the supplementary after in experiments. Okay. So so I found something very interesting when I was reading through this.
6.
Yeah. So here. So this is fine, right? So yeah.
Sorry, which one? I've missed it.
Yeah.
Was it this one?
It was, yes, this one. If you
this
can,
one?
Yes. So so this is very interesting experiment. So you remember we explained about the filters, right? So can you just zoom on block 0?
Yeah. One second.
I don't know whether after discuss this a lot or not, but I found it interesting. So you remember we talked about filters, right? There are filters which responsible for recognizing some kind of features, right? So they did very interesting experiments. First, they're just looking at one block, one layer, and so this is the result if you just train on ImageNet, okay, and then you plot the filter. So filters are exactly at the same location in each of these experiments. So ImageNet, and then if you train on ImageNet 20K, and then on the right side, it will be, if you move a little bit on the right, Aman?
Yeah, doing it
yes.
now.
Yeah, so there is this GFT 300 data set. And what's interesting that depending on the data set or like on how much data you have, these filters look completely different. There is no correlation at all. But for convolutional neural networks, you will see that early, these filters at least in the earlier layers, they look kind of similar, between different architectures. So for example, I personally don't know whether, it's hard. I don't know what to think about this. Maybe there is, it seems like this filter depends on the amount of data sets you train, because there are completely different. So this is I don't know if somebody has some ideas or explanation for this. I found this kind of interesting.
No, I think that really is a good point, that, you know, if like with CNNs, at least then they, like the earlier layers, they're finding top edges, or they're finding top left corners, or like lines or diagonals or whatever. They're just trying to find abstract edges and stuff. But in terms of the MLP mixer, then it's changing there's no such thing that the earlier layers are always finding the same pattern, depending on the data set size. That really is an interesting point that you make there, Dr. Habib. And yeah, it's hard to make of it. I mean, one thing then, does it mean if we apply it on medical imaging, then it will adapt better? I don't know. These are like questions, these are open research questions that should be tried and tested before making any claims. Conscious of time as well, I'll go to all the questions that that have been asked so far. 1 second.
Sorry, yes, let's go to the questions. So Aman, maybe you just want to add one word about this controversy between conv-2D and one-conv-D.
Yeah, I will add it. I've actually got the whole blog post that I released 2 more this morning, so I'll share that very quickly in terms of the controversy. But I just want to also get the questions sorted, because
perfect. Let's go.
Okay, have you tried using this on any present past forms? There have been some kernels that have. I know of them, but I don't know about Dr. Habib if he has.
No, I haven't tried. I'm not brave enough yet to test them.
Hi, Dr. Habib. Aman, why should one change 768 vector to 512? That's a good question, but it's basically, again, going back to the table in the paper. So if we go back to the paper and we go back to basically it's just different architectures. If you want a bigger architecture,
it's a
hyperparameter. Yeah.
You know, think about this as a hyperparameter. And I don't know whether they say, they have, right? We can see
they've got different hidden size. They've got different hidden size. So like they got 512, they got 768, and they've got 1024. So in the bigger architectures, and even 1280. So it's just, you want to change the hyperparameter depending on the architecture. So the bigger the architecture, the bigger the hidden size.
Yeah. Okay, let's go.
The 16x16 patch is flattened, and then it is projected using linear layer to any dimension of our choice. Yes, that is correct. Yeah. That is absolutely correct. You've got this. And then the dimension of choices has been mentioned as in this paper that we just looked into. But you've got this. Why do we transpose 196 by 512 to 512 by 196? So 196 by 5. So the linear layers actually only work along the rows. And you want to mix the channels, and you want to mix the spatial information. So I guess when this is on YouTube, have a go back at when this was being explained in detail with everything. But the short answer is, because you're always mixing the rows. In the first one, you're mixing the channels because every column is a channel. And in the second one, you're mixing the tokens. Have I got this right? Yes, I've got this right. In the second one, you're mixing the tokens because every column is a token. So that's the only reason why you want to do a transpose in the initial one, because in the token mixing, you want every column to be a token. Is there anything you want to add here, Dr. Habib?
No, I think this is very nicely explained.
What does token mixing achieve? Okay. Is this you want to answer? Because I've got a really good visualization or easier way to explain what it achieves.
Yes, please, you do.
Okay. I'm going to use your image.
Whatever you want.
If I can find it. Okay, here it is.
Yeah.
So basically, look at this, right? We started with the image of a frog. Every patch, we don't need the highlighter. Every patch is like this, and the last patch is here. And then every patch is represented as a vector, right? You got every patch as a vector. When you're doing the token mixing, basically, and what you're doing is you're mixing the first channel or just one channel of this token with all the other tokens. So that's the token mixing. So basically what you're doing is you're mixing the spatial information, because it's important, right? We need to know where the eyes are, that the eyes are here in the image. But it does it channel by channel, and the number of channels could be 512, could be 768, but that's what the token mixing does. What the token mixing is doing for every patch, channel by channel, for 512 or 768 channels, it's mixing the information in each of the patches. So you know, okay, eyes are here, or other information is here. So you can mix actually the spatial information as said. And then the next one in the channel mixing, you pretty much take just the one patch and you mix all the 512 or 768 channels in that one patch. So that's the intuition of token mixing and channel mixing. But is there anything you want to add, Dr. Habib?
No, I think we should have explained in this using this short picture. This was very nicely done.
Okay, it just occurred to me to do it that way. Is there a comparison of flops for Mixer versus other architectures? One thing I do want to say is flops is not a good way to compare, because flops doesn't mean that the images, like the architecture is going to be faster. There's like different research papers or different discussions on Twitter that I was reading recently. But in terms of the throughput, when we were looking at the MLP-Mixer architecture, then there was a table that was showing throughput. So I think that's the comparison.
Yeah.
It's not this table, but it's this table.
Yeah.
So see how it's comparing the throughput.
Right.
I am still unclear on the token and channel mixer. Can we review that one more time? I hope, like I just explained it. Does that help, Ramesh? Could you maybe reply to this comment here and let me know if what I just said in terms of an intuition, does that help?
That sounds good. So one question I had follow up. So do you do this token mixer, channel mixer parallelly and then do some sort of concatenation? Or is it like sequentially? You do token mixer first and then
No, it's
token
sequential.
mixer output and then the channel mixer.
Yeah, it's sequential. You do the token mixer first and then the channel mixer. But one experiment you could try is do the channel mixer first and then the token mixer, but I don't think it will change anything, because the idea is to mix both the dimensions, like a 2D kernel, right? Okay, I guess there's a deeper discussion to be had on what exactly goes on in a convolution, but wait for it. I think we might go, Dr. Habib, conscious of your time, it's almost midnight there. Are you still okay to keep going for another 10 minutes?
Yeah, sure. We can just go through all the questions and whatever is remaining, we can go. I'm fine.
Yeah, I just still want to touch upon like what exactly a convolution does and why do we need this token mixing and channel mixing, and that whole controversy which we haven't touched on yet, but I'll go into that. Okay, has there been further work on using MLP-Mixer as backbone for object detection or segmentation tasks? I'm not aware of it if it has been. I think the MLP-Mixer, does it say fine-tuning on other, does the paper fine-tune on? I think the paper in itself fine-tunes, right? Or I'm not sure. The answer is we're not sure. The paper is very recent. It's only a month or two ago.
Yes.
And there's been other works though. There's been more mixed architectures like GMLP, ResMLP. So you could have a look at those as well. There's been definitely follow-up work. If we change the order, exactly, you read my mind. If we change the order of token mixing and channel mixing, I expect it to be. I won't like put the money, like I won't put $1,000 in it, but of course it should be. That's my expectation. What do you think, Dr. Habib?
I think it will be similar.
Yeah,
but you never know.
Yeah, you never know with deep learning. One thing you will see is deep learning practitioners don't know what's happening until it happens. Any ideas on how to do transfer learning to adapt to other data sets? Yeah, you could fine tune. This is still a very same architecture. We could still go and
you just have to, right? So you take last MLP layer, which has for ImageNet is 1,000 classes, and you just freeze. I don't want to say freeze. I think you just freeze depending. I don't know how it will. I haven't done experiments, but usually on CNN you can freeze the backbone and then just fine tune add new NN linear depending if you have 5 classes, and then fine tune the last layer, and hopefully it will work. But we can see on the paper how they fine tune, because they trained on GFT and then how they fine tune, and you can just repeat the same thing with your data set. Okay.
We have one more question. I'm curious to know if you agree with me on the following. One benefit of convolution layers over FC layers is their translation invariance property. Can we say that translation invariance in MLP mixers is achieved since the input is broken into small patches. I did read about the translation in, okay, you go, Dr. Habib. I know you.
So so they proved, so if my understanding is correct, they proved that, you can shuffle. So translation invariance, my understanding is following, that you don't remember the positions. So it means that your prediction are independent of the positions of where things are located. And the nice experiment will be that you just mix, and if result changes, it means it's invariant, or if variant or not variant. So, because you're right, you said that translation invariance achieved because you kind of break down in the patches and then you flatten, and therefore, you connect to fully connected. But, if you think about this, you can take whole image and you can kind of make this one vector, and then you just can have also fully connected layer. And then you probably also will achieve translational invariance. So breaking down in patches and then what happened afterwards, like that you apply nn.linear, I think this all results in achieving this translation invariance. But again, don't quote me on this, please.
Okay, great session. Appreciate the effort. Thank you. Is there any intuition behind why MLP mixers with less number of parameters would require significantly more training data to achieve on par performance with vision transformers? I do have one. I do have a theory, but Dr. Habib, do you have something you want to add?
I will go with your answer.
Okay, I just saw Jan LeCun tweet that when the architectures are less rigid, then when you have lots of data, then you could pretty much get away with less rigid architectures. So that just means that because we pre-training on 300 million, we're pre-training on like a large amount of data sets. Jan LeCun's tweet was basically saying, like, when you have that much amount of data, then you could pretty much get away with an easy architecture. That was the main point, and I think that's the intuition here. That's why you need that much data. That's my intuition. That's what I've read, but I don't have proof. The mixer seems very much like self-attention layer in transformer. Yeah, that's a conversation I don't want to go into. Like, everything then could be broken. Like, one thing is, everything is matrix multiplication, and then everything could be related to any other thing in a similar way. So I think we should be careful when we say, like, this looks like self-attention layer in transformer. Like, you have a query key and value in transformer, and then to me this is very different. But again, we should be very careful when making these comparisons.
Yeah, I agree with what you said. It's there was a specifically point made that this MLP mixer doesn't require attention, and attention layer is slightly different. It has more complexity when you increase the data set, but yeah, so it's not very it's not, I cannot, it's not similar, at least from what I know. And this, the whole point of this paper was that, hey, you don't need attention, you just need the MLP.
Mixing. The main idea is you mix the information in 2 dimensions. I guess that's my main idea that I got from it.
Yeah.
Okay, so now I guess that's it for the questions, but we are still left with the one last thing, is where this controversy is coming from on when the MLP mixer, is that a CNN, or is that a convolution, basically a CNN, and is it a fully connected? So something I wrote this morning and announced on my Twitter is essentially, and it did take me some time, but essentially then, are fully connected and convolution layers equivalent? So when I was reading this paper, I actually asked on Twitter, is there a nice visualization that explains why conv-free and nn.linear layers are the same? The answer is they are the same, and I have the answer now. But the main points, I'll share this blog post as well. 1 second, I'll just post this in the chat, if I can find where the chat is. Okay, so I've just posted in the chat, but the key idea, the answer is yes, conv-free operation. And as part of this blog post, I ended up implementing conv-free operation in Microsoft Excel. So this is how conv-free basically looks in Microsoft Excel. So if you have an input 3x3 matrix, so let's just say you have 3x3 matrix as input, and you basically have, then you say you create a convolution 1D kernel saying you have 3 input channels and 5 output channels. What that means is you have 5 filters, and each filter is of length 3x1 because your kernel size is 1 and your input channels is 3. So essentially you do like a column by column multiplication, like each filter. So for this first column, this filter gets multiplied, then this, then this, then this, then the last one. So you get 5 outputs. Then the same thing happens for the second column and so on. So that's like the convolution operation in Excel. And I compared the results with, basically I implemented this in PyTorch. To compare results, I created like convolution 1D and then the results matched. So that's convolution essentially. In Excel, then you could also implement fully connected layers, which is the matrix multiplication. So if you have your input, but this time you take the transpose, you don't keep the same input, you rather just take the transpose, which is, I'm just gonna convert it like the height to rows. If you take the transpose, and then you still have the same weight matrix. This time it's not 5 different kernels, it's a 3x5 weight matrix. So you do a row by column multiplication, and in a fully connected layer, then you still get the same result. So if like the answer is exactly the same as the conv-1D operation. So I guess the main point of then this blog post is to say that conv-1D, or basically the convolution operation with 1x1 kernel, and the linear layer are the same. Just believe me on that. And if you don't believe me, have a read of this blog post, then you'll believe me. But what I found is that the convolution with 1x1 kernel and fully connected layer are the same. Okay, so let's just stop it at that, and let's keep that in mind. But then if we go into the MLP-Mixer, you see how the mixer has linear layers, right? So it has nn.linear, nn.linear, nn.linear here and here. What if you replace then those linear layers with conv-1D, or just a 1x1 kernel of a convolution, basically a convolution 1x1 kernel? So you could replace all of these with just a convolution 1x1 kernel, and then you could say that the mixer is basically a CNN where the mixer layer consists of convolutions with 1x1 kernel, and that's exactly what Jan LeCun said. So in his tweet, he basically said, "Oh, MLP-Mixer is just a conv layer." I'm opening the tweet as well. The MLP-Mixer is basically just a conv layer with 1x1 kernels. So that's exactly what he said. And like my understanding of this is because the fully connected and the 1x1 kernel convolution layer are equivalent. So you could replace the fully connected. And as part of this blog post, we look at the implementation of MLP-Mixer in PyTorch. And we also pretty much implement the MLP architecture using just convolutions. So this is the mixer layer, which we implement just using convolutions. So we replace every linear layer with a convolution operation and 1x1 kernel. And we see that the output matches that of the linear layer. So you could have all these arguments like, so then that just proves that MLP-Mixer is like a conv layer with 1x1 kernels, but does it really? I mean, so then the controversy is basically like, you could even do the patch embedding, the first part of the architecture, with the 2D conv, which is this part, which is converting the image to the per patch fully connected and to get vector representations of each patch. So that's again also been explained in the blog post, but you could also then use a convolution 2D to do that. So there's like these different ways of doing things because convolution operations are so flexible. But then you could get into all these arguments of, are they the same? Is it just a CNN? But what Dr. Habib and I feel at the end of the day is that it comes down to semantics. So we asked Ross, I pretty much asked Ross Whitman, the author of TIM, and he also said that it comes down to semantics. It's like the deep learning community is split. If you see this as a CNN, that's for you. I mean, that's your interpretation of it. If we see this as a fully connected, that's our interpretation of it. Or like there's no right and wrong. That's what we think. But Dr. Habib, do you want to add something here?
Yes. So, we are, I would say, yes, I think, I think literally I don't have anything else to add, because I kind of agree with like both sides. The main argument is that it doesn't operate like CNN, therefore it's not a CNN. But the thing is that you can use the operation which CNN performs to replicate MLP, right? We can replace nn.linear with const and so on. So the question is like just whether this operation, which are designed for convolutional neural networks, if you replace them in MLP, whether it will convert to convolution type network, or it just you can see the argument in both sides basically.
Yeah.
So yeah, it's up to. I think it's up to you.
In my head, I called it a potato problem.
Right. It's up to you. It's up to you. Maybe we will get after this video. I hope we will not get criticized, but I think it's up to you to decide what it will be. And maybe there will be some, I don't know, maybe there will be somebody will do some experiment and will come up with some solution to this problem. I think it's still not agreed, right? What's happening? Okay, so yeah. Okay.
Yeah, I don't think there's like a common consensus yet.
Yeah,
and that's the difficulty of discussing very recent papers, because you don't know what's going to happen next.
Yes, and we'll be like Swiss people, very independent and natural.
Yep. But anyway, then there's this GitHub gist as well that kind of showcases that you could replace conv-free with linear and all that stuff. So yeah, there's lots of content that we do provide as supplement. Thanks, Dr. Habib, for all the wonderful visualizations. I will go one last time and just have a look if there's any questions on the report, the paper reading group. There is one, I believe. I'll share my screen.
Mm-hmm.
Can you guys still see my screen?
Yes.
Okay. The question is here: on the discussion for FC layers being equivalent to 1x1 convs, see the shared MLP layers in Figure 2 and the code implementation, where the shared FC layers are implemented as 1x1 convs. Oh, okay. Yeah, absolutely. I think there's lots of architectures that implement basically linear layers as 1x1 convs. And I also found an example of this back in 2020 January. Was GPT-2 implementation in Hugging Face, and they were pretty much using conv-free operation instead of linear layers. So yeah, that's being followed quite a few times in the past and has been implemented that way. So with that being said, I guess that's a wrap for MLP-Mixer. Thanks very much, Dr. Habib, for joining us. Really appreciate your time and effort that you've put into the MLP-Mixer, and being a part of this today and sharing your views, sharing your opinions, and explaining things in a wonderful way. And I always, every minute I learn new things from you. So thank you for being a part of the paper reading group.
Yeah, it was a pleasure. Thank you for inviting and like hosting this wonderful paper reading group. I mean, I hope we just have to find some nice paper, and hopefully we can hold one more at some time in the future.
Yeah, absolutely. Look forward to that. Thank you, guys. Thanks, everybody. Bye-bye.
Thank you. Bye.